In this demo, we'll demonstrate how minimal chiseled containers deployed through VCF can improve developer efficiency, company security posture, and produce lighter images that are less costly to run thanks to the newly announced collaboration between Broadcom and Canonical. First, let's jump in the shoes of our DevOps team. Using VCF automation, they can deploy a Kubernetes cluster. If they choose the default configuration, the cluster can be deployed in 2 clicks. However, in this case, we'll use a custom configuration. Here, they can configure various settings. First, we'll set the cluster name. Then they can change any other settings like Kubernetes version, secure key rotation, or storage options. We can now set details for our control plane with the number of replicas, the VM class, and our storage class options. In this case, we'll change our OS to Ubuntu, click Next, and add our node pool. We can keep all the defaults here, and then just change our OS image to Ubuntu. The YAML manifest is simultaneously created as we make selections. We can download it if we'd like to reuse it later or store it in our repository for GitOps. After saving, we'll click Finish and then launch our Kubernetes cluster. Now that our Kubernetes cluster is set up, we need a way to facilitate the deployment of images for the dev team. Our DevOps team can use the power of VCF to deliver Harbor as our container registry service with just a few clicks. We click Add New Service, and then we can see what kinds of services are available. There are various services that you can see here that we can add. In this case, we'll upload the Harbor image that we got from the Broadcom portal and register it as a service. Next, we'll configure this service using the data values file that was obtained from the Broadcom portal. We'll click Finish, and our container registry is ready. Our DevOps job is done, and all we need are a few containers to deploy. Now let's check out our developer workflow. We'll create 2 Python containers using 2 open source tools created by Canonical, Rockcraft and Chisel. The first image will be a regular one, and the second will be chiseled. We will then compare them in Harbor to see how chiseled containers can be up to 70% smaller and much more secure. The first step is to install Rockcraft, which is available for Ubuntu, Windows, and Mac OS. Then we run Rockcraft init to generate rockcraft.yaml. We'll use this file to build our container. There are 2 points to highlight. On line 2, we'll use Ubuntu 24.04 as the base image. In the last 2 lines, we specify the packages we'll need. In this case, base files and Python 3. Those packages are sourced directly from Ubuntu, which guarantees your containers will benefit from the same enterprise security and support available on Ubuntu itself. The next step is to build our container with Rockcraft pack. Once that's done, Rockcraft will generate a .rock file, which is OCI compliant image, compatible with Docker, Kubernetes, and any other OCI compliant tool. Now let's build our chiseled image. First, we install the chisel tool with the following command. Next, we'll search the Python slices we need. Slices are defined as YAML files and detail which files from an Ubuntu package will be used. Slices are not exclusive to Rockcraft. You can use them with Docker files too. Now let's modify our initial rockcraft.yaml file to make it chiseled. The process is straightforward, but there are 3 important steps to highlight. On line 2, we set base to bare. Bare in this context is equivalent of Docker Scratch, which makes our image distroless. On line 3, we set build base to Ubuntu 24.04. In the last 2 lines, we add the slices required by our application. Now we can build our second container using Rockcraft pack. Once the build finishes, we can load our images in Docker using Scopio, which is conveniently packaged with Rockcraft. This will allow them to test their code in their local environment. We're ready to push our images to Harbor for deployment. For that, we first tag each image, and we push them to our Harbor registry. Logging into Harbor, the DevOps team can now see the 2 images ready for deployment. Looking at the results of the full image, we can see it has 16 CVEs and is 42 megs. Clicking on the image, we can see the different CVEs. In the SBOM, we see items like bash, while useful for testing, are not needed in production. Now let's take a look at our chiseled image. It's 13 megs and only has 1 CVE. We can understand why when we look at the SBOM, which doesn't contain packages like bash, making it much lighter and more secure. Hopping back into our CLI, let's deploy the images that we just looked at in the registry. As you can see, nothing is currently running in our newly created cluster, so let's deploy these 2 images. The YAML here points to Harbor and allows us to securely pull the images, but as you can see, the non-chiseled image fails to deploy. What happened? Can a recorded demo really fail? Well, let's have a look at what happened in Harbor. Arbor lets our platform admin team define rules to determine what images can be run. For example, they might decide that any image with CVEs above medium should not be allowed in production and list any exceptions. In this case, the admin found the high severity CVE was a false positive and added it to our allow list. And that's it. It looks like a Kubernetes cluster happily running, but behind it, you have an entire developer, platform engineering, and DevOps setup in place to make sure secure, minimal images are deployed.